Hey everybody. So hopefully before watching this video you had a chance to watch the kinetic molecular theory video that I posted where it goes over just like a brief review of the fact that particles are constantly moving, right? They're always moving whether they're solid, liquid or gas. They're always kind of bumping into each other and moving around. And so that is important as we talk a little more about chemical reactions, right? So we go from kinetic molecular theory into this thing called collision theory. All right, and this is how a chemical reaction actually happens, right? So we have all these particles bouncing around from multiple different chemicals that are our reactants, right? And so the first thing that has to happen is our reactants must collide, right? The two reactants must hit each other, okay? Then they not only must collide, they must collide with the proper orientation, right? So maybe the reaction is happening where a hydrogen leaves one molecule and goes onto the oxygen of another. Well, that reaction is not going to happen unless that hydrogen and that oxygen collide, right? So they have to collide with the proper orientation or the proper, like you know way in space, and then they must collide with the proper amount of energy, right? There is a minimum amount of energy that has to be present there for those particles to actually react, right? And so that can be like a minimum temperature that we need to look at, right? Because temperature is just a measure of how energetic our particles are. And so a way that I always found helpful to remember this, I'm a big Boston sports guy. You can see I'm wearing my Celtic shirt right now. This is David Ortiz. He's a really good hitter, right? And so the three requirements for a home run are the exact same as the three requirements for a chemical reaction, right? The bat has to hit the ball, it has to hit at the proper spot of the ball and the bat, and if you're going to knock it out of the park, you have to hit it with the right amount of energy, right? And the same thing is true for a chemical reaction. Have to collide with the proper orientation with the minimum or proper amount of energy, okay? And so when we talk about energy, energy is present in all of our compounds and our chemicals through their bonds, right? Excuse me. And so that energy is actually stored inside these bonds. And so when we have a chemical reaction, some energy is required to break the previously existing bonds, and then energy will actually be released as new bonds are formed. Okay. And so we have our energy coming in, and then we have energy coming out. And so our chemical reactions can be classified based on if more energy needs to come in, or more energy is going out, right? And we call those things exothermic and endothermic. Okay. Now, I know some of you, when completing a couple of your assignments in the last unit, the questions about like types of reactions, you had mentioned exothermic or endothermic reactions. And what that means in an endothermic reaction, that means overall there is more energy coming in to the reaction. And in an exothermic reaction, that means there's more energy exiting and leaving the reaction, right? So an endothermic reaction requires energy from its surroundings, and an exothermic reaction provides energy to its surroundings. And it's easy for us to tell which is which because an endothermic reaction will be cold and an exothermic reaction will feel hot to us. Okay, and so let's see an example of this here with a combustion reaction. This is the combustion of methane, right? CH4. And so energy is overall going to be released in this reaction, right? Combustion we can associate with burning things, right? And so obviously if we're burning something, energy is being given off, right, in the form of light and heat. And so energy is being released in this reaction. Where is that coming from? Well, that is coming from the the formation and the breaking of bonds, right? So it takes a little bit of energy to um, to get that reaction to happen, right? We have to put some energy in to break up those methane bonds, but then there's a lot more energy being released when these carbon dioxide and water bonds are being formed. Okay, and so we can actually graph this energy change over time, and we're going to do that now. I'm going to use my scribble tool. Okay, so we can see we're starting with our reactants here and our products down here. Okay, and so if I have the energy of my reactants, I have to heat it up or provide some sort of spark. That's my activation energy. And then energy is being released from my chemicals. Okay. So what we're seeing here is we could look at a graph of temperature over time and it would be different. We're starting with something that is higher in energy and ending with products that are lower in energy. So in this reaction, we are having energy being released, right? We're ending at a lower spot of energy than we started. And so That is the fire and the light and the heat that would come out of this exothermic combustion reaction is this energy right in here, right? Now this activation energy, that is this energy right here, right? The minimum or the proper amount of energy. That's what this little hump is right here on our graph. That is the energy required for the methane and the oxygen to actually react together. Okay, and so we can visualize that if we're thinking of like a reaction with a gas like methane. That would be the spark, right? That would be the match or the lighter that we would have in order to start that reaction. So when you're going out to your grill, right, to cook some burgers or hot dogs or whatever, some corn on the cob, right? Um, that you can open up your propane tank, but it's not just going to react as soon as it hits the air. It needs a little spark, right? You have to ignite the grill in order to get that to happen. Same principle here. Okay, and then we know that that energy is being released because that energy is being used to cook your food. So okay, this reaction is exothermic. We would, if we were placing the energy in our chemical reaction, we would place the energy on the product side, right? Because energy is being produced overall, and so our products are going to be lower in energy. They're going to be more stable. Things that are higher in energy are going to be less stable, right? And that's why that reaction doesn't take much of a spark to occur. We also have the opposite that can occur in an endothermic reaction. Okay, so let's scribble here. So in this process, I have baking soda and vinegar. And so what happens when we put those together is those components will immediately react with one another, and they actually get their energy from outside sources. So you can see here our energy is actually increasing over time. And so if we were to touch a a reaction of baking soda and vinegar, it would feel cold to us, right? And that's because this reaction is actually absorbing and taking energy in from its surroundings. And so since that heat would be leaving our hands, it's going to feel cold to us. Okay. And so here you can see that we actually have less stable products up here than we do the reactants, right? The reactants are lower in energy here, so they're more stable. Our products are higher in energy, so they are less stable. And this is a reaction where energy is entering, which is why we call it endothermic. Okay, so you have an assignment over this where we look at this actual reaction and we talk about it a little bit, and it gives you some time to play around with where these products and reactants should go. Okay, so check that out. Thank you for watching.